Shalom. Shalom, folks. 1,000 apologies for being so very late. First, I want to thank Warren Bray, a new Patreon. Oh, we're going to look at some problems, huge problems for the globe. See, okay, when I first sat down to draw the map of the Earth, there's very little information. How do you draw it? What's the sun? What parameters are you going to use? How are you going to determine which are justified and which are not? And this is how I realized that the sun wasn't what the sun is supposed to be according to the mainstream flat Earth idea, a small orb in the sky, and certainly not a distant orb. So I realized first, to be taken at all seriously, we're going to have to have information that's better than the globe information, because the globe information is false, but you can have a series of false statements and then a whole series of true statements, and as long as the true statements are the ones that are considered for observations, then the false statements slip in as if those were true also. So I realized that not only was I going to have to reconfigure the thinking regarding the sun, but also cosmology. And that's what today's hangout is going to be about. But first, I'm going to share something. And this is to do with maps. I'm going to be having a debate with a globe link regarding my map, and he's a cartographer. That's right, a cartographer. So, or a geographer, anyway. Just bear with me while I sort Windows out. Greetings everyone in the chat. I see everybody was really enjoying the chat being open and just being able to just chat nice and relaxed. Okay, so what I'm going to do is I'm going to screen share this. Okay, so what is this? Oops, just hit the wrong thing. Oh, get the images, don't want a copyright strike. Go back. Close. Okay, what are we seeing here? We're seeing a globe. Come on, stop messing. We're seeing a globe atop a Freemasonic hall or a Masonic lodge. Okay, come on, computer. Okay. Oh, it's not wanting to play with me. There you go. This globe. Okay, this one here. We're seeing the famous Freemasonic emblem of the set square and compass above a globe Earth. You might note over to the left is South America. To the right is Africa. You might notice those, I don't know, 6,000 miles between them, between the closest points. You see the huge distance, that huge Atlantic Ocean. These are Freemasons. You would think that Freemasons, more than anybody else, would know the distance between the continents and how to depict them on a globe, given that the globe is a Freemasonic idea, right? And I'm saying this in preparation for my debate with the cartographer, because I'm going to ask him, he's Spanish by the way, Catalan maybe, no, Spanish. I'm going to ask him why these huge discrepancies and why move South America around so much. So I just wanted to show that. Okay. Now what's this? Yes, here we're going to see video evidence of the same. Okay, you have to forgive the big weird thing that happens. There you go. Now we're also going to look at Australia and how close it used to be to South America. Oh, there you go. There's Australia, and here's South America. If you measure the size of Australia, east to west, approximately 2,500 miles, that would bring it approximately 3,000 miles away from South America. Oh, but this is only a globe just for a movie company. It's like, yes, but remember what I just showed with the Getty images? Okay? Somewhere in the back of that is Australia. And, well, between Australia and Africa and Australia and South America, there must be some distance. So, problems for the globe. Okay? Now, I'm also going to pause it here. This is how, when I first studied geography at school, many of the people listening, you will remember having seen a map with this configuration, with South America more south of North America instead of more southwest. Okay? So we have on the screen, we have, let me display the other style so you can see my cursor. Okay. Ugh, a horrible display style. Right. Oh, come on. Oh, this thing, I swear to God, it's driving me nuts. Right. That's right, that's why I'm nuts. Okay, so, pause. Go back a little bit. Right. We have Florida. Okay, here's my cursor. We have Florida here. Between Miami and Quito is just here. Between Miami and Quito, well, if this was the configuration, you would have to fly south west. Okay, you would fly down and to the left to arrive at Quito. Okay? Not down, just straight down, and certainly not down and just ever so slightly to the right. Well, now it's down and ever so slightly to the right. Wanna see? Bear with me. Except, you see, there are these things in the real world called compasses. Okay? So I'm going to pull up the grid so that you can see the so-called longitudes. Can you see from here, ever so slightly, look, from here, from Miami, wait a second, just there, okay, got it. And now Quito, in Ecuador. And this is an Ecuadorian who showed me this, okay? Here is Quito. Can you see how we've crossed over this line of longitude here? We've crossed over from Miami to Quito, okay? Just slightly southeast. In the real world, the compass reading, once you have corrected for declination, takes you to approximately here, which means Quito is here, okay, where I'm showing. Okay, which is also what this is showing. Dagnabbit. Pause. There. Okay. South, west, see, this way. This is how the world used to have South America depicted, and this is how we were first taught it at school, and this is how the real world is. Obviously, it's not a sphere, it's like my map. Google Earth tells you have to go over here to land in Quito. But what the heck is this globe? Well, it's a globe used by artists for Universal Pictures. Obviously, you're seeing it right there. This is a legend of the Holy Universal Pictures logo history. There you go. That's what this is. Just a whole series of all their logos. Great. So, in the last century, there have been pretty drastic changes to South America. Good gosh, you think it would all be pretty well set, right? Well, no, not at all. Here we're seeing, again, the huge gap between the two. And here we have a huge gap between the two. And here too. This huge gap between Brazil and Africa. Huge gap. But enough about that. Let's now go, and this was just prepping for the globe link. This is the subject of today's hangout. I'm going to stop displaying this style, that way I can join you in the chat. There you go. No. What am I doing? Video capture. Oh, what am I showing? What am I showing? Oh, right, okay, I'm just watching on the screen, see what's... Okay, apologies folks, I have the wrong thing set up. Just a second. I am not well. That's why the ultra late start. It was, you know how they say the best laid plans of mice and men? Well, that wasn't even well laid plans. It was pretty kind of hastily, kind of optimistic plans. Yeah, I'll set this for 11. That way I will definitely be up and at it. And nope, fever says otherwise. But not important. Okay, here we go. We're going to listen to this. This is Methuselah. Okay, remember what I said. First, the sun is not the thing that we've been told it is. You have to figure out what it is. You have to look and make observations and go, wow, okay, that's peculiar. And develop an idea of what it is. So you can explain it, so you can test it. So that would be a theory. And then you have to look at cosmology and do the same there, because the globe idea, you know how the globing say, well, what about the stars? What about the stars in the north and the stars in the south? What about the celestial poles? What about all these things? It's because they have a model installed in their brain that says things about the sky at night. That's what it says to them. It scrolls around, therefore we must be rolling. That's their idea. Now, if we develop a theory that is better, that you can test and that you can prove, and that answers more questions than it poses, then that's what's going to win this battle. It's not going to be maps, it's not going to be discourse, it's not going to be people in the street saying, oh yeah, it's flat. None of that. It's going to be a better interpretation of the world. And there are flat earthers out there who say, we don't need a better interpretation. Okay, you fine, you go your way. I'll go mine. I'm the one that's going to change the world. Sorry. I just said that. All those who change the world are the ones that think they can. So, I'm going to show this video, I'm going to show you what it's called. A star that's 200 million years older than the universe. That's why I've called this older than one's mother. So we're gonna play it. Let's see what this farce is, because it's a farce.
The oldest
come on.
star in the universe. It's 14.5 billion years old, a number that's difficult to get your head.
We're gonna go back to the beginning, and I'm going to just dissect every single word this clown shoe says.
Meet HD 140283.
What's that? It's a light in the night sky. Oh, very good.
Or Methuselah.
Good. It's better. Methuselah, easier to understand. It's just better than HD 140283. You know, you could call it a god if you wanted to.
The oldest star in the universe.
Wait. there slips a little bit of gibberish. The oldest star in the universe, we're going to see how that's just perfectly wrong and perfectly false, and how that star destroys their model. Because you see, their model says this: light is this thing. If we stratify what this thing is, microwave radiation, if we stratify it, we can check different bands. So we can separate it into different bands, and we can check different bands, and we can see which of those bands are being received by our telescopes. And then we can determine things about that light. So we can determine whether it's moving away from us, whether it's moving towards us, its age, its composition, all of these things, which are all of them false. Yes, the telescopes do receive radiation. Yes, you can stratify that, but when you've based your idea of light on a theory that's false, then your results are going to be false, patently false. And when they receive these results, instead of going, dude, our model is crap, our model doesn't work, instead they try to justify them. Watch.
It's 14.5 billion.
Here they're saying how old it is. No, it isn't. You haven't got a clue how old it is.
Years old.
You don't know what it is, never mind how old.
A number that's difficult to get your head around. After all, our universe is only 13.8 billion years old.
Wait, what? So that star is older than our universe, is it?
How is this even possible?
How is this even possible? See, neurolinguistic programming is... you should all get Richard Bandler's book. It's very good, very interesting. Instead of saying, but wait, this is impossible, you instead say, how is this possible? You see? I'm going to show you.
A number that's difficult to get your head around. After all, our universe is only 13.8 billion years old. How is this even possible? How can anything...
You see all these hows? No, it's very simple. That's impossible. Never mind the hows. Never mind your hows. But wait, you're saying that person is older than their own mother? But how's that even possible? It's like, no, it's not possible. That person is not older than their own mother. You understand?
Have appeared earlier than space, time, and the whole universe.
So, I'm gonna do a lot of this going back and going over. Older than time itself. Huh. Then it couldn't have any kind of system that's registering an age that's older than the universe's age. It would at least be showing the same age as the universe.
0.8 billion years old. How is this even possible?
Wrong question. But isn't that impossible? Would be a correct question. Or even, that's impossible, which would be an assertion. A correct assertion. It's impossible.
How can anything have appeared earlier than space, time, and the whole universe?
It can't. Not according to your model. So your model is wrong. And now we're going to hear some of the ways how they've tried to wrap their heads around seeing evidence that their model is wrong. Just seeing it. It's like, wait a second. According to the systems we've been using, our model is full of crap. It's wrong, it's broken, it doesn't work.
Scientists have been observing Methuselah for the past 100 years.
Not true. They say scientists have been studying this for the past 100 years. Like, you don't know how long scientists have been looking at this light. You have no clue.
Until recently, very little was...
I want you to notice a little visual neurolinguistic programming of stars moving around. Watch.
...known about this star, only that it's located 190 light...
You see how there are stars moving around to show parallax, which doesn't happen in the real world?
...years from Earth in the constellation Libra, and penetrates outer space at a speed of 800,000 miles, or 1.3 million kilometers per...
Yeah, you know how our sun is supposed to travel at 500,000 miles? Yeah, well, that one's apparently 800,000.
Per hour. This was pretty much the sum of our knowledge about Methuselah, and the star itself did not cause keen interest for many people.
By the way, just so you all really take this in, the grids that are being shown, all of the visuals that are being shown, they've not just been created by a video creator just for a laugh. They've been created as a system of programming your mind for when you're considering space.
However, everything changed dramatically when, in 2000, astronomers attempted to measure the age of Methuselah. According to early estimates, it was a record 16 billion years old. Scientists could not believe that this was at all possible, so they decided to conduct further research. Howard Bond of Pennsylvania State University, along with his colleagues, collected more than 11 sets of observations that were obtained between 2003 and 2011 using Hubble's fine guiding sensors that record the positions, distances, and energy of stars.
Well, that didn't work.
In addition to this, for 6 months, Bond studied the parallax effect, that is, the change in the apparent position of a star relative to the distant background.
Wait a minute. Relative to the distant background? It can't have a background if it's the oldest thing in the universe. If it's the oldest thing in the universe, it will also be the most distant thing in the universe, and there would be nothing behind it to be a background against which to show parallax.
In reference to the position of the observer, this allows you to better calculate the ratio between...
So you're seeing all of the parallax. See what I was bringing attention to? All the movements of those little lights. That's congealing. That's to congeal the idea of distance between stars in a three-dimensional space universe.
Between the brightness of the star and its distance from the Earth.
Oopsies, they've got the Earth rotating the wrong way. I'm going to go back.
Distant background in reference to the position of the observer. This allows you to better calculate the ratio between the brightness of the star and its distance from the Earth.
So, ratio between the brightness of the star and the distance. Scaling invariance kicks in, and not only that, but none of the distances that are explained for the stars work versus light. Light is something that we can study, and light says, well, at those distances, not visible. So what the globe believers do is they make the stars bigger, as big as they would have to be in order for us to see them, but they have a problem because if they're that big, then the radiation that would be received is much, much higher than it is. So instead, they do this mathematical trick where they just add zeros. They add zeros and then ask you in the mathematical equations regarding the radiation that's arriving to either add or subtract zeros, just, fudge.
The older the star, the dimmer its light will be. During this study, Bond could not justify the earlier estimated age of the star, so he supposed that mistakes were made in the previous calculations. Initially, the age of the star was measured by the rate of nuclear reactions.
Now there's a problem. The rate of nuclear reaction? No. And this is the thing, that star is emitting a consistent spectrum. Oh no, but nuclear reaction doesn't produce a consistent spectrum. Never mind.
The faster the star consumes hydrogen in the core, the younger it is. With age, instead of hydrogen, helium is formed, acting as stellar fuel. Therefore, after 1 billion years, a star loses some of its brightness. Methuselah is rather dull and estimated.
So, after 1,000 years, a star loses its brightness. Well, let's now consider the starry sky at night as seen by humans 1,000 years ago. Would it be all of those stars brighter?
To to have burned hydrogen for about 16 billion years. True, this method of calculating the age of a star cannot be considered accurate. This led scientists
Because it's giving an impossible result, so it's not accurate.
to look for other clues that could prove that Methuselah might be younger. After some time, scientists still found one sign that most likely indicates a younger age for the star. It has to do with oxygen. In the early universe, it was practically non-existent, but in Methuselah,
This, in the early universe, it was practically non-existent. Like, in your fairy tale, you mean? In the fairy tale of the universe starting from a Big Bang and all of that impossibility. In that universe, it was almost non-existent. Tell us some more.
the ratio of oxygen to other elements was quite high. The increased oxygen content, together with all the other indicators, allowed scientists.
Now, there's a little bit of word salad there. In the early universe, oxygen was almost non-existent. However, Methuselah had a heck of a lot of it. Listen.
The ratio of oxygen to other elements was quite high.
See? So, in the universe, next to no oxygen, Methuselah, quite high oxygen, gonna go back.
Might be younger. After some time, scientists still found one sign that most likely indicates a younger age for the star. It has to do with oxygen. In the early universe, it was practically non-existent.
In the early universe, it was practically non-existent.
But in Methuselah,
But, however, okay, so but, however, Methuselah,
the ratio of oxygen to other elements was quite high.
isn't that contradicting what you said a minute ago about practically non-existent?
The increased oxygen content, together with all the other indicators, allowed scientists to lower the estimate of the present age of the star to 14.46 billion years.
Wait a minute, isn't that based on your idea of when oxygen started existing? Like, there was a time oxygen didn't exist. That's right, yeah, and then it started existing. Oh, that's lucky.
But this still doesn't explain the phenomenon, because this makes the star 660 million years older than the...
Wait a minute, the phenomenon? That's the wrong use of the word.
The increased oxygen content, together with all the other indicators, allowed scientists to lower the estimate of the present age of the star to 14.46 billion years. But this still doesn't explain the phenomenon, because this makes...
He just threw that word in there. The phenomenon? No, that's not the word. That's wrong. The observation, it still doesn't explain the observation. It still doesn't explain the existence of the star. But the phenomenon? No, that's incorrect use of the word phenomenon.
Makes the star 660 million years older than the universe. But research...
So, 660 million years older than the universe. That's right.
Researchers didn't stop there. They continued to try to get to the bottom of this mystery. In 2014, another study was conducted.
So, they keep taking readings, and the readings keep saying to them, your theory's wrong. Get over it. But they keep saying, no, we'll look in a different way. And they look in a different way, and they go, the results say, your theory's wrong. Get over it. But no, we'll look in a different way again. So they look in a different way. Results, your theory is wrong. Get over it. So they check in a different... It's never going to be different to that. Their theory's wrong.
That reduced the estimated age of the star even further to 14.27 billion years. Given the margin of error in the calculations, the star is about 14 billion years old, which still makes it 200 million years older than the universe. However,
However, never mind however, that's impossible. Impossible.
Calculations, the star is about 14 billion years old, which still makes it 200 million years older than
And that's still impossible.
the universe.
And that's still impossible. Makes it older than the universe. That's impossible. That's like somebody being older than their own mother. Not possible. But instead of actually again saying impossible, he says, however.
However,
Oh, that's an easy way to get around that. However.
Howard Bond considered that the error could be greater, which means that the star is perhaps younger and
However, because this is saying your model is wrong, get over it. This guy said, no, I think the star is younger because it's impossible for it to be older, so it must be younger. That's what it must be.
and appeared immediately after the Big Bang. This could have been the end.
So let's go back to what this guy just invented. He said, well, it must be this. Listen.
That the error could be greater, which means that the star is perhaps younger and appeared immediately.
And also, perhaps, which means that the star is perhaps. Well then, when you said which means, that's undermined by the word perhaps. Like, which means that the star is obviously, then that's fine, but which means that the star is perhaps? No, you've undermined the meaning of means. So I'm going to go back and play again.
Than the universe. However, Howard Bond considered that the error could be greater, which means that the star is perhaps younger and appeared immediately after the Big Bang.
Did you hear that? So the star is younger. It's not older than the universe. No, it was born at the same time as its mother. Immediately at the start of the universe. Yeah, universe started, boom. Star started too.
This could have been the end. But
this could have been the end. I don't think so. That's a cockamamie. That's just broken. But this is a universe. This is the universe. This is the lights in the night sky saying to the cosmologists, your theory is wrong. Psst. Your theory's wrong. You have to drop it.
But there's another study that simply shocked astronomers and perplexed the entire world.
I don't think it perplexed the entire world because most people have never even heard of it, so it's not really.
According to information obtained in 2013 by the Planck Space Telescope, the universe can only be 11.4 billion years old, not 13.8.
Oh, that's even worse.
Similar conclusions have been based on the expansion rate of the universe.
Well, we know about that being all a cockamamie idea. Yeah, we can see how old the universe is because we can look into its past, but it's its future.
Until the end of the 20th century, physicists believed that the universe was expanding at a rate of 41.63 miles or 67.4 kilometers per second.
Oh.
Given this indicator, scientists obtained an age of 13.8 billion years.
Now, I'm going to go back to this. This is the Hubble constant, the rate at which the universe expands. It's like, you might sit and go, so the blackness of the night sky and stars, and with instrumentation, you can see that there are more stars than the ones that are just visible to your eye. That's interesting. And we have this pre-existing theory that it all started at one point and has been expanding from that point. So it must be expanding at some speed, right? So let's figure out how quickly it's expanding. And along comes this guy and says, this is how quickly, see, this is the math I did, see how it all ties up. There you go, that's what it is, right? Like, true story, like, this is what they do. They just make stuff up, make math, say what they've made up in mathematical terms, and say, see how the math ties up? Well, that means it's true. It's like, look, you can develop a theory that says that tap dancing seahorses are making all of the stars and all of the planets, orbits, whatever they're orbiting, just by the wake of the tap dancing seahorses making little circles through space. And you can then translate that into a mathematical equation, despite the fact that tap dancing seahorses don't exist.
Miles or 67.4 kilometers per second. Given this indicator, scientists obtained an age of 13.8 billion years. But
hey, let's measure the infinite. Well, if we measure the infinite, we're never going to end. Well, let's say that we can measure it anyway.
According to a newer study, the speed is approximately 45.9 miles or 74 kilometers per second.
So, somebody, we're talking the world of cosmology and astrophysics. So you have all kinds of ideas that were posited by people who, well, pre-existed the newer people. And the newer people come along and go, I think I can tweak this a little bit and get my book on the book, get my name on the books. Yeah, I can tweak it. I might even, if I tweak it sufficiently drastically, I might even get a Nobel Prize.
According to these numbers, the universe is...
Remember, according to these numbers. Not according to this truth, according to these numbers.
It's only 12.7 billion years old.
Oh, that makes it even worse for Methuselah.
Then, scientists made even more accurate calculations.
So, the universe was thought to be of a certain age. And people said, no, I think I could change that, so they changed it. Somebody else came along, I think I could change that too, and they changed it too. And then other people came along, I'm going to change it further, so they changed it further. That's all that's going on.
And it turned out that the universe is expanding even faster.
There. Going to go back to listen to that little sneaky NLP.
0.7 billion years old.
The clue is, it turned out, which is a very matter-of-fact thing. It turned out.
Then, scientists made even more accurate calculations, and it turned out that the universe is expanding even faster.
Did you hear it? Slipped in there. Scientists made more precise calculations, and it turned out from their calculations, not from the observations, from their calculations, that the universe is, well, not even that age.
At 50.95 miles or 82.4 kilometers per second, which means it's only 11.4 billion years old.
Oh, that's even younger now.
The expansion rate of the universe, the so-called Hubble constant, can be calculated in two main ways. By studying the relic radiation and by measuring the distances between galaxies.
Did you hear that? Yeah. See the radiation? Yeah. Well, if we say that this amount of radiation means this amount of time, then, well, the first word there was if. If we say that this amount of, see?
In the first case, the Big Bang itself provides basic information.
It does, and that's just an idea, remember.
After this grandiose event, which gave rise to everything, light was left behind.
Wait a minute. Methuselah was still there, wasn't it? It was already there, pre-existing the Big Bang. Don't forget that bit, because that's what you're talking about. You're talking about Methuselah. 200 million years older. You're now talking about the Big Bang as if you're not talking about Methuselah. You're talking about Methuselah. So the Big Bang started. Methuselah was already there. So I'm going to go back just so we notice that clever little twist.
Big Bang itself provides basic information. After this grandiose event, which gave rise to everything,
didn't give rise to Methuselah.
Light was left behind, which scientists call the cosmic microwave background, or relic radiation. Astronomers have compiled extremely accurate maps of this background, which allows us to simulate the early universe, its composition, and speed of expansion.
No, it doesn't. It doesn't allow for any of those things at all.
By the second method, astronomers collect data from galaxies, stars, and supernovae. These objects change their luminosity.
Now, the word was data. What he's referring to is readings. Okay, so instrumentation, receiving readings. Look at all those filaments, by the way. And this is CGI. Instrumentation receives readings. Those readings are taken as data, and then the data is computed. But if the readings are arriving from a source that's completely distinct to what the theory of the course of those readings is, then the theory and the data and the calculations are all going to be completely off, which they are. You know, because you have this star that's older than the universe. Not possible.
As they move further away, so that you can measure the speed of the expansion of space. This is where all the inconsistencies begin. According to the first method, the age of the universe corresponds to the number that you'll see if you search on Google or Wikipedia. That is 13.8 billion. However, in terms of the second method, space and time are a couple of billion years younger. Perhaps our universe, during different periods of its existence, simply expanded at different rates of speed. Only none of the existing theories today are able to explain this.
Of course, because the theories are wrong.
The fact is that the expansion is influenced.
Now listen. The fact is. That's what he just said. The fact is. It's like, no, that's not a fact. You're talking about a theory that's demonstrably wrong, and all your so-called facts come from a wrong theory. So I'm going to go back and listen again.
Expanded at different rates of speed. Only none of the existing theories today are able to explain this. The fact is that the expansion is influenced by dark energy.
The fact is that the expansion is influenced by dark energy.
The opposite force to gravity.
The opposite force to gravity.
True, no one knows for sure what this mysterious force actually is.
True, nobody even knows what this mysterious force actually is, nor do they know what gravity actually is.
But physicists were always sure that it was constant. But if this were so, the rate of expansion would also remain stable throughout the entire existence of the universe, which is not what we observe. So, it would seem as if we have missed something.
So it would seem like we are wrong. That would be the honest thing to say. But then your career in cosmology and astrophysics ends. If you say, we're wrong, and all of you guys are wrong too. All of you are wrong. Yeah, you're wrong. We should really start developing a different cosmology. Oh, dagnabbit, here's a flat earther who's doing it already.
There's probably something that can influence dark energy. Physicists...
Oh, let's go into that.
What we observe. So, it would seem as if we have missed something.
By the way, notice how he says it would seem, which is a bit kind of wishy-washy. It could be just a little... It could be just an appearance thing. It would seem that maybe we got things wrong. It's like, no. It's obvious that we've got something drastically wrong.
There's probably something that can influence dark energy.
So, there's probably, we need something that can influence this, so we're going to make one up. We're going to make a thing up that can influence this dark energy.
Says Massimo Cerdonio from the University of Padova tried to figure out what exactly causes our universe to be so unstable. He's focused on the fact that dark energy is
Right. Again, he's focused on the fact that tap dancing seahorses, what?
Largely dependent on quantum fields. Each similar field is assigned a separate type of particle.
Hey, what's a field? It's in the Book of the Sun. I explain very clearly what a field is. In the Book of the Sun. They don't know what a field is. They just use the word field without actually knowing what it is that they're using.
And extends to all of space-time. For example, all electrons belong to the field of electrons.
Oh, that's a bit like saying all theology belongs to the field of theology. All cosmology belongs to the field of cosmology. All bakery belongs to the field of bakery. All road digging belongs to the field of road digging.
And neutrinos, respectively, to the field of neutrinos. The energy arising from the interactions of these fields determines the expansion rate of the universe. However, when physicists try to calculate the energy of all existing quantum fields, the result is a number 120 orders of magnitude greater than the calculated amount of dark energy.
Good Lord. Well, there's another glaring sign that the universe is saying, you've got it all wrong.
Therefore, Massimo Cerdonio suggested that there must be a special particle, unknown to science, capable of influencing dark energy and the entire universe as a whole.
And therefore redressing that 120 orders of magnitude. So, they have this idea. Hey, if we say that there are fields, hey, what's a field? Never mind that. If we say every different little element, it has its own field. It's part of its own field. When we look at the exchange of energy between those fields, good Lord, it all goes really wrong. Right. What if, so a lot more energy, right. What if there's some kind of particle or something that consumes that energy? Yeah, it just consumes that energy and therefore brings it down from 120 orders of magnitude more than what we receive to what we receive. Brilliant. It's just one great big tap dancing seahorse. Yeah, it just consumes all that extra energy.
Is a number 120.
It then converts that extra, it needs to consume all of this extra energy to convert it into telepathic thought that is then picked up by all of the other tap dancing seahorses, which are in the same field, so that they maintain the orbits of all the different things in the sky.
Orders of magnitude greater than the calculated amount of dark energy. Therefore, Massimo Cerdonio suggested that there must be a special particle, unknown to science, capable of influencing dark energy and the entire universe as a whole.
He means a particle that consumes all that extra energy. That's what he's talking about. Which would be a particle field that consumes all that extra energy.
True, the presence of such a particle has been predicted in earlier research.
So, true. Like, no, not... right. True. Somebody said that this would be the case. Okay.
In the field of physics, and has even been given a name, Axion. Presumably, this particle appeared immediately after the Big Bang, but has remained hidden for billions of years and did not manifest itself in any way. But
wow. Another glaring, like, this is a klaxon call saying your theory is wrong. Yeah, this is other thing, but it doesn't manifest in any way whatsoever at all. Yeah, just whenever we need it to correct a mathematical problem, yeah, that's when we'll conjure it up.
Recently, the Axion has gained influence and has changed the entire field of research about the development of the universe.
This doesn't mean the Axion has started exerting an influence on matter in the universe. No, just influencing the ideas of the cosmologists and astrophysicists. That's right.
With its quantum field, thanks to which we can no longer accurately say when space and time itself arose.
Now, that's a pretty significant statement there. We can't say when space and time arose, which means we can't say when the Big Bang happened, which means we can't say what the hell the universe is. We can't say what the black of the black sky at night and those stars are. Listen.
Development of the universe with its quantum field, thanks to which we can no longer accurately say when space and time itself arose. This leads to curious thoughts. If the universe is expanding faster than it did 13 billion years ago.
If. And if not, then what? Well, never mind that. We'll cover that next year.
Does this mean that time is also passing at a different speed today?
Oh, sooner or later, astrophysicists are going to confirm what I've been explaining in the Book of the Sun and what I'm explaining in the new book. I mean, this is going to happen, folks.
That is, would 10 minutes in the 21st century be different from 10 minutes at the dawn of the universe? It's rather difficult to answer these questions without ambiguity. But whatever the answer, Methuselah still remains older than the universe.
Now, when it says it's difficult to answer these questions without ambiguity, it's like, no, it all depends on how you frame your argument. You can make it absolutely robust and not ambiguous. Yeah, but if 10 minutes was less than 10 minutes now, or if 10 minutes was more than 10 minutes now, well, nah, then you're introducing ambiguity. But if you say the amount of time that 10 minutes was in the past is of a different quantity or different measure than it is now, then it's not so ambiguous.
At least it will be so until scientists solve the mystery of dark energy and its elusive particles.
Now remember, all of this is about Methuselah, which pre-exists the universe. So all of this is a way of trying to get around that impossibility. All of this word salad, all of this filler, to try and get round that impossibility.
Still remains older than the universe. At least it will be so until scientists...
Right, going back.
That is, would 10 minutes in the 21st century be different from 10 minutes at the dawn of the universe? It's rather difficult to answer these questions without ambiguity. But whatever the answer, Methuselah still remains older than the universe. At least it will be so until scientists solve the mystery of dark energy and its elusive particles.
So, we still have this star that is telling us our theory is wrong until we patch up our theory with something that, without disturbing the other things found in our theory, other calculations, influences specifically the age of that one star. It can't be something that affects everything ubiquitously. No. It has to affect only that star and make it send a different time signature. And that's why we misread it.
True if, after all future calculations...
Notice again, true if, like, and if not...
this star remains the oldest in the universe, maybe then there...
He's now said true if, after all the calculations, this star remains the oldest in the universe. Like, wait a second, no. If, after all calculation, this star remains older than the universe itself...
was something else before the Big Bang. What do you think about it?
I know he's asking for ideas. Have you got any ideas, guys? We just watched from Riddle. 2.8 million subs. A star that's 200 million years older than the universe. And at no point did he say, this shows that our theory is wrong. This demonstrates our theory to be wrong. This is showing that our theory is wrong. This is showing that our cosmology is wrong. At no point did he say that. Instead, he sidestepped it by saying, however, and but. Now I'm going to screen share black page while I join you in the chat. There. True story, folks. This is the cosmology of the universe that says that we live on a sphere. That's that cosmology. Yeah, we live on a sphere. Right, why do we live on a sphere? Because everything becomes spherical because of Big Bang and stuff. Oh, right, that's interesting. You got anything that confirms that? No, we've got things that contradict that all over the place. Oh, really? Don't you have anything that confirms it? No, we have nothing that confirms it. We've got all kinds of things that tell us, no, that's wrong. Hey, everyone in the chat. Let me see. Oh, Gleam still has a wrench. I'm going to have to take that off you. I'm taking that off you. No offense. By the way, I meant to share this with you. By the way, I just said, because I've got this, sinusitis. You know, pressure in my face. Got face ache. So when I saw this, I thought, I'm going to share this with Gleam. I'm going to pass this to Gleam. Give him a good chuckle. Oh, Miles Davis is in the chat. So Miles Davis is a globe link. He will have been in the chat and either had this video muted, so he doesn't actually have to hear any of it, or just dismiss it, which is what globe links tend to do. Ah. So there's this Miles Davis character who doesn't really quite grasp the concept of level. Okay, Globalings don't grasp the concept of level because, well, you can't have both level and a right angle at the end of an observation on a sphere. Let me see if I can pull up just simple triangles. Yes, triangles again. I'm just going to write triangle in the search. Triangle. Google wants to know my location. I just got a message. Google wants to know your location. What for? Well, we just want to know. What for? Right. Let me do triangulation instead. There we go. Wonderful. Wonderful. So in a previous video I showed why the method for triangulating is bisecting. Aha, I have one here. This will do. Only it's inverted. Sorry, 1 second. I'm looking for a good diagram to show on the handout. It's funny when you see when you know what they're trying to hide. It's funny when you see them trying to hide it. Here I have it. Okay, so let me share this just a second. This goes to Miles Davis and the other Globalings. Oh, wrong one. There we go. Okay, okay. So we see there the simplest derivation of the Pythagorean theorem. Ow. So you have a right angle there. You've got this 90 degrees right up near the little corner. It's like, that's not where the 90 degrees goes. That's over on the other side, silly. But never mind. Let's go to another triangle. I was looking at the one on the right then. There you go. It's a simple one. This one on the right. Chapter 7, test angles, triangles. Okay? Now, see that right angle right there? We're looking at the one on the right. That right angle for an observation is impossible on a globe. That's right. It's just simply impossible. Why is that, Antonio? Well, because the corner on the left, where it says 506 times 309, okay? The corner on the left there, that's a point of observation, and there's a distance between that and the right angle. And it does not matter what that distance is. It could be a millimeter's distance. It will still show a divergence in the vertical lines used to establish the location and the distance. Okay? It will show, well, the radius, line B, going straight down, which is what makes a right angle, is at a different angle than the point of observation. It's impossible on the globe, no matter what the distance. And the greater the distance, the more acute the problem. So I will show how the Globalings try to get around that or try to disguise that, okay? Here. This is how they try to get around that. Okay? Point 3 is the point of observation. You're measuring you've got this baseline. Forget that. We're not looking at that. We're flipping it. We're looking at angular resolution of an object in the distance. Okay? So we're going to take point 3 as the point of observation. And you've got the unknown distance. That's fine when you have an unknown distance. As long as you've got a known size of the object. Or vice versa, if you've got a known distance and an unknown size of the object. Great. You notice how this triangle, half of it would be underground if you're measuring an object in the distance, because you have the horizon there. And you notice how if you were looking at a stellar object where you don't have the horizon in the picture, you can still triangulate by projecting a right angle using the simpler triangle that I showed a minute ago. But this way, when they do this, they can dismiss altogether the fact that the 90 degree, there would be where the unknown distance meets the baseline, that's where the 90 degree would be, that would necessarily be at an angle pointing away, where the top is pointing away from the observer. That's right, in the real world, geometry tells you the Earth is flat. And then there are people who can just intuitively figure that out, go, no, that's not right. But at school, we're told, no, this is how you do it, and if you don't do it like this, you will fail. So people just repeat. Oh, what's this? New paper from NASA about the solar Parker probe. We did not expect it to be this turbulent. Oh, right. I'm going to pull that up. From Gleam. Let me see, where's that gone? Right. Just a second, folks. I'm juggling windows in the dark. So close. Make that small. Don't forget, by the way, okay, we're not talking triangles. We're not going to show what Gleam has just shared from NASA. Oh yeah, this. So I'm going to play this too. I haven't seen it. It's going to be fascinating. Right. So I'm going to share another one, and then I will bail. Give me a second. Well, we didn't expect these things. But yeah, no shit, Sherlock. Right. So I'm going to screen share this. Thanks, Gleam, by the way. Right. So let's listen. Make sure I've got the volume up. This Russian dude, it's like, he's pretty forthright with what he says. I mean, obviously he says a heck of a lot of stuff that's just part of the theory and just definitely wrong. Like, Earth's geomagnetism, yeah, it comes from the molten iron core. Oh, really?
Seen recent discoveries coming from NASA from this beautiful Parker Solar Probe. Let's talk about what they've discovered, and welcome to What the Math. NASA launched quite a lot of very interesting missions, but one of the more interesting recent missions was, of course, the so-called Parker Solar Probe. And just like previous solar missions that NASA has launched over the years, the Parker Solar Probe is essentially meant to investigate the activity very, very close to the actual surface of the Sun. But
really? They sent a little thing to the holoprismatic Sun that isn't even there anywhere? Yeah, well, no, they sent it to the gaseous mass in the globe fantasy. That's where they sent this thing. But they will have taken readings from the sun because they have to present something to the world.
Like other
And when I say the sun, I mean the radiation that comes from that great big bright thing in the sky. That's a holoprismatic phenomenon.
that mostly are responsible for just looking at the sun and looking at various effects, the Parker Solar Probe is of course different. And what makes Parker Solar Probe so different is of course the fact that it's going to be the closest object to the sun that we've ever launched. In other words, unlike other probes that are just looking at the sun, it's going to actually try to physically experience what it's like to be so close to this beautiful object. The closest approach is going to happen in December of 2024, so essentially 5 years from when I'm making this video. And if you are watching this in the future and it's December 2024, cool. Anyway, so this is what the probe sort of looks like. This is the simulation using Universe Sandbox, and this is what the sun is going to look like when it approaches it at a distance of about 7 million kilometers, which is
December 10th, 2019. Now, either I'm having a fluoride moment, or that's 4 years, not 5. Because he just made this video like this month, and it will do this flyby in December 2024. That's 4 years.
About 4 times closer than the distance that it currently has. In other words, it's actually going to move a little bit closer. Now, if you don't...
Now, sorry. It was a fluoride moment. Ignore that.
really know much about the orbital dynamics or basically how orbits work in space, well, all you need to know is that it's going to be using Venus, which is right here as you can see, to try to lower its orbit even.
It's going to use a light in the sky to try to rebound around that light in the sky. True. That's what they say.
More than it currently has. So in other words, it's not really using any engines. It's not using any kind of fuel or very, very little fuel to try to basically move as close to the sun as it can. Now, there's an old video I made many years ago explaining how this works. Essentially, this is known as the so-called gravity assist or the gravity slingshot maneuver. And you can see how Voyager right here used this maneuver several times to try to gain as much velocity as possible. So this is a very well-known phenomenon to us, and we usually use this for craft to use the gravity itself as a way to accelerate or decelerate instead of using actual fuel. So, in about 5 years' time, Parker Solar Probe is going to discover a lot of new things about the Sun, but even now, NASA has already released 4 new papers describing some of the very unusual findings, and very surprising findings. Now, in a nutshell, what the NASA has discovered is that this nearby space, very close to the Sun, is an extremely different environment, as we kind of thought it would be, but not to the extent that we imagined. And in some sense, NASA even compared this to a kind of a waterfall and river phenomenon.
Right, so they imagined that the conditions in that region of space near the Sun would be X, but it turns out it's even more different than X. It's more different than what they imagined.
So in other words, let's just say that somewhere right here, this is going to be Earth, and what we're seeing here, the flow of water, is basically most of the solar system. And the water itself here represents various solar wind and magnetic interaction created by our Sun. In other words, it's the flow of particles and various solar winds generated by the Sun itself. So where the probe is right now would be equivalent of this, the kind of a bottom tip of the waterfall, whereas this here would be the surface of the Sun. So it's seeing all of this extreme interaction happening in real time and has discovered some unusual properties of the solar wind so close to the Sun itself. So first of all, it discovered that the wind itself is extremely fast here. As a matter of fact, when the...
Hey, wait a second. It's not explained why it's not melting. But never mind that.
Probe was passing through the wind, it seemed to have discovered winds that were 15 to 20 times faster than we anticipated. So the actual particles move here at up to about 50 kilometers per second velocity. And it also discovered these unusual, very kind of strange and very large waves that you can see are being formed which the scientists refer to as a kind of a solar tsunami. So basically here it passed through these waves, through these reversal waves.
By the way, can anybody say filaments?
That were detected by the probe and were,
even though this is a NASA graphic,
exceptionally powerful and very, very large in size. These are a type of what's known as an Alfvén wave, which are essentially waves formed by the interaction of various particles. This is what we thought they're going to look like, but instead they looked much larger and much more extreme. And on top of this, not only were these waves really large, there was also a lot of turbulence here, with speed suddenly changing quite dramatically. In other words, the waves themselves would suddenly accelerate or decelerate by up to about 300,000 miles per hour, or about 450,000 kilometers per hour. And all of this would happen almost instantly, within only seconds. So this is a very turbulent, extremely powerful environment. And because of these sudden unusual changes in speed, the scientists believe that maybe this is why the coronal region, this...
Please don't be fooled into thinking that the image you're seeing on the screen is like video from this mission, okay? This is just CGI of a different type.
Region very close to the sun is so exceptionally hot. It's actually several thousand times hotter than the sun's surface itself.
But it's still not melting. Yeah, that's right. It doesn't melt. It's made out of armor of God.
In other words, if you were to look at our sun and if you were to look at this region right here, it would be millions of degrees as opposed to the sun's surface that's only a few thousand degrees. And so NASA scientists think that maybe it has something to do with these turbulent regions that they just discovered. They also discovered some of the more unusual properties of the way that solar wind is generated, and it seems that it's a lot more hectic and unpredictable than we thought. We thought it was kind of like more or less equivalent everywhere. It sort of spreads just like you expect the water here to spread, more or less sort of...
This is a very poor analogy, by the way, I have to say.
...peacefully and across the entire river, whereas in reality it seems to be really hectic. There seem to be these holes all over the sun's surface that release a lot of different solar wind that does spread across the entire area and then sort of adds up to creating the solar wind that we observe here on Earth. And at the same time, so close to the sun, the solar wind also seems to be spinning with the sun. In other words, as the sun rotates, so do all of these solar particles and solar wind very close to the sun. And then eventually, as it reaches further points, that's when it separates from the sun and then begins being transmitted across the rest of the solar system. But in these close regions, several million kilometers away from the sun, it seems that everything is sort of attached and spins with the sun itself. And just like everything else in this region, it's more or less magnetically connected. So these are not gravitational connections, these are all electromagnetic connections that are formed by the very strong magnetic field so close to the sun. At the same time, it was very surprising for the scientists to discover that apart from having large emissions, like for example what we would call a solar flare, which would be very large and very easily visible from Earth, there also seem to be these really small emissions, very small flares that we never would detect otherwise. And the Parker Solar Probe was able to see these small emissions, very tiny flares that don't really affect Earth.
Right. The video he's showing now pre-exists this probe. The video you're seeing now, where you're seeing those tiny little bubbly flares, he's saying we wouldn't have even detected them. Well, yeah, unless you looked at this video.
Almost at all, but do produce enough emissions close to the sun, thus affecting some of the nearby regions. It might actually affect planets like Mercury and even Venus, but doesn't really affect Earth at all. Another unusual discovery was that throughout its time close to the sun, at a distance of about 24 million kilometers from the sun, the craft was actually being bombarded by various tiny particles. And NASA believes these tiny particles come from various comets and asteroids that came a little bit too close to the sun and essentially got destroyed over time. In other words, there's a lot of material that's being sort of evaporated and released from various asteroids, like this series right here that I just added in Universe Sandbox,
Wow.
that then produce this gas that spreads across the solar system. And the Parker Solar Probe was able to detect all of this. But the simulation I created here is actually...
That's interesting, that all that dust from disintegrated stars are just hanging about. You know, you think it would have been like pushed away, you know, from whenever it is the the comets were disintegrated. Yeah, you think it would? No, it's just hanging about, it's just loitering. Yeah, it's travelling very fast, but it's loitering.
A little bit unrealistic because the dust I added is a little bit too close to the sun. One of the major discoveries from Parker Solar Probe so far is that there seems to be a dust-free region denoted by this ring, this orbit right here that you see. This is about 5 million kilometers away from the sun, and there's basically no dust here. Everything is or has been evaporated and destroyed, so all of this is pretty much empty of matter, or actually the only matter that is here is coming from the sun itself, possibly things inside the solar wind. Nothing in here is from the rest of the solar system, but it's very likely that even at its closest, the solar probe will never really reach this region to explore it a little bit more. So in other words, the probe will always have a little bit of dust hitting it and will never be in dust-free region. Now, these are not the only discoveries, but I think these were some of the biggest ones, and I'm sure there will be a lot more in the next year or so as the probe gets closer and closer to the sun itself. And the reason it's going to take basically 5 years for it to reach the closest part of the orbit is because it depends on Venus to lower its orbit, and so it actually has to align its own orbit that you see in white here with the orbit of Venus that is in yellow. And so basically by timing the orbital alignments, that's when the probe gets to experience this slingshot maneuver that I mentioned previously, and that's how it gets to come closer and closer to the sun. Now,
so remember what he was just explaining about the dust around the sun and all of that they're experiencing, even though it hasn't actually got there to do that. Yeah, well, it hasn't actually got there to do that, to experience any of that. That's interesting.
In the next 5 years, we'll probably find a lot more about the sun, but the most important part of this whole mission is, of course, for us to learn more about the solar wind and how our sun is able to generate these solar flares and everything else that affects us here on Earth. As I mentioned in one of the previous videos, I personally believe that solar flares are literally the most dangerous thing that can happen to our society today. So by studying the solar wind and how solar flares are generated, the Parker Solar Probe will hopefully allow us to find a way to prevent a serious disaster from striking planet Earth. If you haven't seen the video I made previously, check it out on the channel as well. It should be popping up somewhere above my head. But essentially, this here could one day end our civilization. Solar flares are extremely dangerous. But anyway, we'll talk more about this in some of the future videos, and most importantly, we'll talk more about the discoveries of the beautiful Parker Solar Probe in some of the future videos as well. If you haven't subscribed, subscribe. Maybe share this video with someone who loves learning about space and sciences, and come back tomorrow to learn something you may have not known before.
Right, okay. What is that thing made of that it doesn't melt? I mean, it obviously melted in order to be fashioned into that shape. Are you understanding, Globelings? Look, all of those metal things were fashioned, so smelted, melted, and formed into components that could be configured into that probe. So they do melt, but somehow they don't melt. Oh, I thought that there might be actual real data there. I think it's all of it just fantasy. All of it. Anyway, there you go. Thanks for that, Gleam. Jeez Louise, the fantasies these guys come up with. Yeah, what about it not melting? Never mind that. It's made out of magic. Also, that sun, yeah. Blood is thicker than water is pointing out that's a fantastic sun. Yeah, it's absolutely amazing. Yes, Gleam writes or coalesce with gravity like planets supposedly form. I thought mass attracts mass. Oh, not when it doesn't. Mass attracts mass apart from when it repels mass. Yeah, so I'm now going to go into the chat, address anybody who's making comments to me, and then I'm going to bail. Have something. Face. Most of our planet realm is water. Yes, water makes level. Level is flat. How are you, Antonio? I'm very well, thanks, man. Yep, but no, not according to the globe. The water's spherical. Yeah, it's just a spherical because the gravity. Oh, okay. What about this star that's older than the universe? Well, never mind that. Filament. Right, it's Cosmic Surfer. Liam writes, true, I even saw a real video of Jackie Chan stealing it from some Amazon tribe. Yeah, Armour of God. That's right, that's what that's made of. So they calculated not accounting for this massive tsunami of EM radiation, but they reckon they're going to get that slingshot effect from gravity regardless. Yeah. So, we're on our way to Venus, to slingshot around Venus. We're getting a heck of a lot of winds that might, change our trajectory, but never mind that. We're still going to do it. Alright, are you? Gleam, I'm not going to look right now, man, but that's just funny. He writes, do you know about Starlight? It was a hairdresser who discovered it, and supposedly the formula died with him. Look up Wiki Starlight. Yes, but first I'm going to go and take some painkillers and stuff. Alright, folks, thank you very much. I hope you enjoy this thing. Yeah, just remember, according to cosmology, it's a star that's older than the universe itself. Yeah. And that's not the universe saying, no, your theories are wrong. No. That's just fact. According to them. Fact. That star's older than the universe. Let's figure out how that can be the case. No, it can't be, silly. Okay, thank you very much, folks. Shalom. Bye.